Okay, that's great. Thanks a million, Phil. So thanks everyone for coming this morning. My name is Ronan Daly. I'm the head of data analytics here at Surf, and I'm going to talk to you today about some of the tools we developed here at Surf and previously at Polyomics, and how we use them to help perform some high-level data analysis for researchers at University of Glasgow and elsewhere as well. So imagine, if you will, the timeline of a scientific experiment. So here's a sort of a very small, I guess, and crunched up way of thinking about it, but we often start off with an idea of some sort. We conceive of perhaps an experiment we'd like to do, and then after that conception, we want to try and design the experiment in a more formal manner, and making sure that we think about all the factors that might be important in the experiment and perhaps the way we might measure these things. After this design, we actually run the experiment, we execute it, and then perhaps we get the samples and pass them to maybe people at Surf. We get measurements from that experiment, and then we come up with some initial data processing. So this is where we take the data and we do some looking at the data at a sort of bioinformatic type level. And then after that, we try to do some more further data analysis. We're trying to really explore the data in some way, come up with some more hypotheses, perhaps come to some conclusions about the experiment. So the data analytics part at Surf really is concerned with the design and the further data analysis of experiments. So as you can see here, here are some of the things that we actually do in terms of this. So as I said, mentioned, the design of experiments here is very important, and we like to talk to people as early as possible when they're designing the experiments to make sure that they can get the most out of what they're planning to do and the most out of the money that they're going to spend. But most of our work is generally done on the further data analysis or the downstream data analysis. After much of the analytical work and the bioinformatic work has been done, we're here to sort of probe the data in a deeper manner and trying to get some big conclusions out of there if possible. Now, the analysis we do is mainly based upon omics type data, so your transcriptomics, genomics, metabolomics, proteomics, and so on. And the type of methods we use are kind of in a realm of mainly statistical inference and machine learning type methods. Most people tend to want something to do around the realm of statistical inference, so we're doing things like t-tests and so on like that. And oftentimes we're trying to do tasks as biomarker type selection, or maybe something like a disease modeling type task, and maybe like a classification or regression type model. And of course, we also help with training as well, and we're also here to help write up some grant applications and write up results from the analyses that were done already. So a little bit about us. My name is obviously Ronan Daly. My background's mainly in computer engineering, in AI, machine learning, and my experience tends to be in stats and computational typology. And I also work here with Andrew, and he's got more biological background with genetics and so on, and he's quite experienced there in meta-analytics and tool development. So if we drill a bit deeper down into the offerings that we provide for data analysis, like I mentioned before, we often are interested in talking to people upfront about the design of their experiments, because if we can get that design nailed down correctly at the start, it definitely helps with the follow-up analysis later on. So we like to talk and have a discussion to find maybe the factors of interest that could be interesting in the experiment, and also the confounding factors that might be present in the experiment. These are quite important because by capturing the confounding factors up front, we're going to make sure that we can adjust for these factors later on when we have to in statistical type analyses. And of course, nowadays, a lot of the research councils, especially things like the MRC, are very, very interested in power analyses because they want to be able to judge the correct or necessary sample size to support a particular conclusion. And oftentimes people haven't got as much experience doing these power analyses in omics type studies, so they might need a little hand in being able to calculate the number of samples that are necessary. And we're very happy to help with that if we can in these types of situations. In terms of statistical inference there and biomarker selection, we'll do the sort of gamut of what people expect for these types of tests. So like t-tests, ANOVA type modeling as well. And we also do things like linear modeling as well, if people want something a bit more sophisticated. We're very interested in obviously putting in the covariates that we've measured up front, making sure that they're accounted for and adjusting for correctly in our statistical models. And feature selection obviously is something that's very, very important to lots of people. We want to be able to find the most important features in your models that can explain perhaps your phenotype of interest in the most parsimonious way, but also the most powerful way as well. And sensitivity analysis is actually quite important as well. And this is where we're trying to make sure that the conclusions we're coming out of at the end of our analysis are actually quite robust. So it's very important to be able to make sure that these results that we're finding out are going to translate out into the wild in some way. So I'm going to talk a bit about some of the software design and then some of the actual analyses that we've done for people here. So one of the pieces of software designed quite a few years ago now actually is our metabolomics pipeline that we use in-house in Surf, and also people can use it on their data that they generated here at Surf as well. And in this here, we're able to go really from and analyze the data from the raw files up to pathway type analysis later on. So it's really the whole range of analyses that can be done in a single web application. And it's a very, very useful type of piece of software to examine, the peaks that we have in the data, but also then the sort of biological interpretation later on. And here's a piece of software I call Graphomics here, and this is really a data integration type platform. And people want to use this. It's actually up at the moment on the web. And the idea is that we can take different types of omics data, so for example, transcriptomics, proteomics, metabolomics, and we can pull them all together into a single analysis and enable people to get a sort of holistic overview of how these various omics are connected to each other. And it's underlined with a Reactome database underneath, which is sort of modeling these connections via reactions, and then these reactions that are grouped into the pathways. And by doing so, we can get a sense of if something is changing at one level, how does that affecting other things that are changing at a different level? And by doing so, we get a much better picture of how our data is actually looking overall in a sort of integrative type manner. And so actually, it's interesting. We actually have used these tools on analyses here that we've done. Here's an example analysis here that we've done here. This is with Hinglung here at the Beatson. And in this case here, we have a sort of mouse model here, and we're autographed sort of human tissues. And the idea here is that we are running some untargeted and then some untargeted metabolomics, some proteomics, some RNA-seq. And we're trying to integrate these data together to get a mechanistic understanding of what's going on inside this model system that we developed. And by using the Graphomics tool, we were able to actually see this mechanistic understanding here of what was going on. We could see in this case here how we have the changes in NAA is cascading downstream and affecting other subsystems inside the system of interest in here. And by doing so, we're able to make that mechanistic model, that real connection that's underpinned by actual evidence and underpinned by knowledge, to make sure that we can really make a very good and sound conclusion about how our particular experiment is actually working when we have two different types of cancers. And by doing so, I think the results are very, very robust and very, very reliable, and it works quite well in that situation. Here's another example of an analysis we've done here. This is hypertension, and we're looking in this case at how salt affects hypertension, but irrespective of blood pressure. And so we're looking really at protein catabolism. And in this case here, we're able to help make sure that the analysis that was done was actually quite robust, because we had obviously a lot of features coming up, but they weren't being corrected for multiple testing. So by making sure that we were using the correct multiple testing type procedures, we could show that the features that were picked out at the end were actually robust and statistically sound. And by doing so, then we can sort of make sure that the results that were published in the paper are actually robust as well. Okay, some more of the offerings that we offer here at Surf. In terms of machine learning, we do the whole gamut of normal machine learning, or I say orthodox old-style machine learning type tools. We do clustering and hierarchical and flat clustering, regression and classification of all different types of models that people would want to use. And most of the time, people just like to do simple type models such as lasso and so on. We also have projection techniques, obviously, like the simple things like PCA and multidimensional scaling, and maybe things like T-SNE or UMAP and so on. Being able to visualize data in some way that makes sense to people. One thing that we're very, very interested in and very, very think is very, very important is the idea of validation. So making sure that we're not overfitting our machine learning models to the data. And this can happen quite easily if we're not careful. So we're always making sure that we are doing validation of sorts, generally internal validation, by using, I say, a cross-sampling, validation or bootstrapping type method, making sure that the results coming about will generalize out into a wider population. And another thing we're actually quite interested in is interpretable machine learning outputs. So making sure that we are able to understand how the model works, even though it's a kind of a black box, how the various features interact inside the model and how that affects the outcome of some sort. So by using interpretable machine learning methods, we're able to get a better understanding of how these models are actually working from the outside. In terms of disease modeling and classification, oftentimes physicians and so on are quite interested in these types of models because it gives them something that actually is actionable in some sense, that we can say that this could perhaps be used in a clinical setting of some sort. And the general types of analysis we do are ROC type analysis, of course. Logistic regression is very, very useful for these analyses because it's quite interpretable. We often do things such as comparing these omics type sort of analyses to clinical type measures, such as just general clinical measures, perhaps there are imaging as well, just to see how they're actually stacking up against what's actually used at the moment. And sometimes we see that the clinical measures are performing perhaps even better than the omics type measurements, or sometimes the other way around. And we don't really know until we actually do the comparisons. And as I said before, sensitivity analysis, robust conclusions are very, very important in these types of studies. It's something that we're very, very careful about and making sure that the results that we're presenting are robust and generalizable and actually will be useful in a general setting. Some more research we had done previously is on pathway analysis, and for pathway analysis or metabolomics, actually, there was never quite a huge amount of tools out there. We developed a tool ourselves in place here that was able to perform this type of pathway analysis on metabolomics type studies, untargeted metabolomic studies using LCMS type systems. And we're actually able to find that this works actually quite better than other types of systems that have been developed mainly for transcriptomics type analyses. Metabolomics data has generally its own type of idiosyncrasies, and it means that we have situations such as missing values and so on that can make the interpretation of the data difficult in pathway type analysis. So by developing these tools, we're able to get much more robust and better pathway analyses out that people are often quite interested in. And here's another type of application that we developed. This was, in this case, one of these little chip type applications where we took a sample and we were able to drop that sample onto a chip and then it gave a readout of various metabolites. And the idea then is those would feed directly into a classification type algorithm and enable physicians at the bedside to be able to give a diagnosis perhaps of, say, cancer or not cancer. In this case, it was prostate cancer. Now, in this case here, we were able to help the researchers in developing a robust classification tool. At first, they were overfitting their tool to the model, or overfitting the data to the model that was coming out. And that was causing results that were much too optimistic. By looking and by performing better robust machine learning type approaches, we were able to help make a more robust outputting tool. In this case, it was a random forest classifier, and make sure that the results that were coming back were actually indicative of what we were seeing in the general population. Another application that we were working on was the idea of being able to see, look at arthritis in this case here, and the effect of various drugs on arthritis. In particular, in this case, there was rheumatoid arthritis, and we're looking and seeing how does the application of drugs in this case here give us an output of some sort, and how does that change the various metabolites of interest that we're thinking about in terms of disease activity. So in this case here, disease activity is showing how bad a disease is, and we're looking to see, can we model a change in disease activity in terms of changes of the various metabolites that were in a sample. And we saw in this case here that we're actually able to make quite a good relationship between the idea of itaconate and disease activity, and we were able to come up with a pathway type model that explained how this would work here in organisms as well. Something a little bit of fun here. We were actually asked to do analysis here of some Burns manuscripts. So Robert Burns obviously was a poet here in Scotland quite a while ago, and a very, very important poet. And so important actually that there were quite a lot of forgeries of his documents. And obviously these forgeries, the documents are quite a lot of money, so the forgeries were in circulation to try and make some money. And the idea was, can we try and classify whether a manuscript was a Burns or a forgery by looking at things such as the ink and the paper and so on, by using a surface type of LCMS, a surface type of mass spectrometry system. And by doing so, analyzing the metabolites and coming up with a classifier of some sort that would give us an analysis and give us a readout of, is it more likely to be Burns or more likely to be a forgery in this case here. So by doing so, we're able to come up with classifier systems in this case here that were able to give us a look at certain metabolites and how they interacted with each other, and give us a really good output, or a fairly robust output, onto various questions about the provenance of manuscripts that have been given to us. So other tools that we developed so Andrew was able to come up with these website here, Digitally, and this is sort of a meta-analysis type website. We're able to find genes of interests for fruit flies and able to perform this analysis here of interest, given your data perhaps, and also by using other online resources as well. And finally, one of the big tools we had developed quite in the past was the idea of being able to help the understanding of metabolomics type data by designing this in silico mass spectrometer. And the idea was that we were able to design a system that would able to increase the number of fragmentations that we were getting in our mass spectrometry LCMS system, and by doing so, get better identifications of the metabolites that were coming out of experiments. And we were able to design the system and actually run it and test it and validate it on a real LCMS type runs, and we were able to show that we were able to get better fragmentations and better data out the end, that we were able to perform much better identifications for the metabolomics data, and that would help then people analyze their data in a much better manner. Okay, so to summarize, what can we do? Well, we can help you design experiments if you want to. We're also able to analyze complex biological data using statistical and machine learning type methods. Generally, we're interested in analyzing multiple omics layers and other data types as well, if you have those too. And we can train classifier and regression tools, not just for omics data, but that is mainly what we work on most of the time. We're able to partner up on grants if you're thinking of putting machine learning or a large analysis portions inside your experiments. Talk to us and we'll be able to help design and write out some of the grants text that might be useful to come up with these ideas. And then we're also interested, obviously, in providing training and helping write up the results at the end of an experiment as well. Okay, so that's everything. Thanks very much for listening, everybody. If you do have any questions, I think the Q&A box perhaps is the one to write them up in, and we'll do our best to answer them as soon as possible.